In this section, we're going to start to look at, or we are going to look at, the transition metals, and in specifically the transition metals and their colored compounds and why they're colored. Now, we are going to be kind of springing ahead to some things that are in the next lecture, some things that are in the next unit even. And so I'll be touching on some topics, and I've made reference to it in the notes in terms of we'll be coming back to these again later on when we get to subsequent lectures, okay? So know that we're going to be revisiting some of the stuff in here. A lot of the compounds that we run into, just before I start the note, end up being most of the compounds, most of the ionic compounds, many of them, that if they don't contain a transition metal, are just white crystalline powders. And when they form a solution, they form colorless solutions. It is the transition metals that form these colored compounds. Okay? And so, as I've said here, most compounds contain only main group elements are colorless or white crystals. And that's because only the much higher energy orbitals are available to receive an excited electron. So when an electron absorbs energy to go to a higher energy level, the ion does not absorb visible light. And so we're talking about complementary colors, and we're going to talk more about what that means. Those of you who have taken art know what I mean in terms of the color wheel and the complementary colors of being on the opposite side of the color wheel and that. And so the complementary wavelengths or colors to the absorbed energy is still not in a visible spectrum. So we don't see the stuff that's coming through, and so therefore all of the visible spectrum wavelengths get through, and because of that we see it as white, because that's what the white means. So ions of transition metals may be found in complex ions or as the primary cation in a hydrated compound. We've talked about that a little bit before. And in these cases, the metal ion forms a complex, either with nonmetals, like oxygen, or with water in something like this penta-aqua copper 2 ion that I've got here. And that's not the only one. The ones we're going to focus on are going to be the hexa-aqua, those types of compounds or complexes that have 6 coordinate covalent bonds to the central metal atom. And the reason for that is it forms a structure called an octahedral. It's one of the shapes the additional shapes we're going to talk about when we get to the HL bonding in the next unit. And we're only going to be looking at the splitting patterns for the octahedral crystals. There are other splitting patterns that are out there, and I mention it here, but they're not a focus of this course. Okay? They're very specific on this one. So whether they form a complex either with a nonmetal or with something called a ligand, and water can be one, but ammonia can be one, and so on, in either of these forms, the d orbitals split. So you know that we have 5 d orbitals, and they split from being what we call 5 degenerate orbitals. Degenerate orbitals means they all have the exact same energy, to 2 distinct levels where some of the orbitals have higher energies than the other orbitals. And the split that we're going to focus on here, the exact splitting pattern, as I said, is dependent on a variety of different factors. For the IB diploma program, we'll focus solely on the splitting pattern of a complex that has 6 electron domains. That's the way we refer to it now. That's the terminology you will see throughout your program from here on in. Electron domains, which is essentially electron pairs, whether they're lone pairs or bonding pairs. We refer to them as electron domains, around that central transition metal ion, and that yields an octahedral shape. And as I said here, we'll revisit that idea of an octahedral shape later when we get to the bonding unit, because there's a whole pile of additional shapes that you're going to learn this year. If you know anyone from the pre-IB class this year, they are learning those shapes in pre-IB. We've decided to shift those shapes down. So you guys will learn them later on. Now there's a variety of different theories, and if you have the Oxford companion guide. I know that I've seen a few people in here that had that big, thick, soft-covered companion guide. And if you happen to have that companion guide, they go through a little bit of history in terms of the different theories that have come up with over the years to try and explain why these particular set of elements form these colored complexes and their bonding and everything else. The one that we're going to focus on is called crystal field theory. And so that's the one that we're going to use to explain what's going on here. It's only one of, I think there's 5 or 6 listed in that companion guide. Okay? So according to that theory, the 5D sublevel orbitals in an octahedral complex split into 2 sets. 3 orbitals decrease in energy. These are called T2Gs. They are stabilized. They have lower energy. Lower energy is more stable. So they are called the stabilized sublevels or orbitals. And 2 orbitals go up in energy, called the EGs. And these are destabilized because they are increasing in energy, and the higher energy is less stable. So you get 2 orbitals that are destabilized because they increase in energy, and 3 orbitals become stabilized and drop in energy. And now you have 2 distinct sets of D sublevel orbitals, 2 with the higher energy, 3 with lower energy. They're no longer degenerate. Within the splits, they're degenerate. So the 2 EG orbitals are degenerate with one another. The 3 T2G orbitals are degenerate with one another. You understand what I mean by that? Okay. What we're going to talk about today all falls back to this next point, that the energy separation between the orbitals, or these sets of orbitals, is what we call the crystal field splitting energy. And everything kind of wraps itself around this idea that the greater the split, the higher the energy, and that's going to change the color that we're going to see. And the lower the split, the lower the energy, and again, that will yield different colors. So the different colors that we see for these complexes is based on how far apart the T2G suborbitals and the EG suborbitals are from one another. Okay? There are 3 different factors that we're going to look at that dictate what the crystal field splitting energy will be. And so in terms of memorizing, I've said before, we don't memorize chemistry, but realistically there is some memorizing. We've seen that because the information we take in kind of fits into basically 2 groups or 2 classifications. There's simple knowledge-based information, and we have to memorize that. And then there's information that we use that's more of a problem solving, and we don't memorize problem solving. We memorize the base stuff, we don't memorize the problem solving. And so there are trends here in terms of what we're going to look at, and we have to know and memorize what those trends are because we can then use that to answer more complex questions. Okay? So the 3 factors that we're going to look at is, number 1, the identity of the metal ion. Number 2, the oxidation state of the metal ion. And number 3, the nature of the ligands that are bonded to the metal ion. Okay? And at this point, I always get students that go, and here's the sort of the big question is, why do we want to know all of this? Why do we care? Okay? And as we're going to see later, the colors of these compounds is directly related to the energy that's absorbed when an electron jumps from the from the stabilized orbitals to the destabilized orbitals. You see, when we pass light through that compound, whether it's through the crystal or whether it's through a solution that contains these metallic ions in solution and these complexes in solution, the complex will, because of the metallic ion in there, will absorb certain wavelengths of energy to allow the electrons, a electron, to jump from the T2G stabilized up into the EG destabilized orbitals. And because that jump is not that high, it doesn't have a very high energy, it is actually in the visible spectrum. So what we're actually doing is absorbing visible light wavelengths, and what we will see are the complementary colors, which is essentially the colors that aren't absorbed. So when you see something like yellow, what it means is whatever you're looking at that's yellow is absorbing the wavelengths that aren't yellow. And so the wavelengths that get through are yellow. And so that's what you see. Or if you see black, it means it's absorbing all the wavelengths of visible light, so there's an absence of any visible wavelengths, and so that turns out to be black. And if you see white, it means that none of the visible wavelengths are being absorbed, and you're getting the entire visible spectrum, and when it all mixes together, it becomes white. It becomes white. Now, if you don't believe me, you don't trust me on this one, you can, if you have a colored printer at home, you can, I've got the color wheel in this note, in color, okay? And if you have a color printer, what you can do is you can cut out that color wheel in a circle, okay? And if you can somehow secure it to the end of a pencil or something like that, if you were to spin it rapidly, those colors on that color wheel would meld together and it would become white or very close to it. So all I've said here is that the greater the separation, the greater the energy required to go from the stabilized to the destabilized, and we can then directly relate energy absorbed to the color we're observing, or we can directly relate the color we're observing to the energy that was absorbed, so vice versa. So first thing we're going to look at here is the identity of the metal ion. And in general, that separation energy increases as we descend within the group with subsequent metals in the same oxidation state. So if I was to go, for example, from let's say I was going to go from nickel down to palladium, as long as I kept it in the 2+ ion, then the palladium should have a higher separation than the nickel in the 2+ ion. Okay, so that's what we're saying. As we descend in the column, provided we have the same ion charge on the two ions, that the separation would get larger, and therefore the colors that are absorbed would be from higher energy wavelengths within the visible spectrum, and what we would then see are the lower energy wavelengths that are left over, that aren't being absorbed. We'll talk more about that in a little bit. If we're talking about the same metallic ion, so let's suppose, for example, we're looking at copper. For any given metal, the separation increases as the oxidation state increases. So there should be a greater separation for Cu2+ than there is for Cu1+. So the same metal with a higher oxidation state will have a greater separation. Reason for this has to do with how close the ligands are to the central metal ion. So it necessitates that I go through, at least on a cursory level, what a ligand is. And a ligand is a molecule or an ion that has a lone pair of electrons that it donates to a coordinate covalent bond. Coordinate covalent bond, both electrons come from the same atom. So it's got to be either a neutral molecule like water, or something like the chloride ion, which has 4 pairs of electrons around it that you can donate 1 pair to a coordinate covalent bond. And the metal ion complexes involve ligands bonded covalently to this central metal ion. So, again, we'll discuss this further in the next lecture. So since the interaction between the ligand and the metal is electrostatic, it's positive-negative type of interaction, as the charge on the metal increases, it is going to decrease the distance between the ligand and the metal, because those electrons are going to be pulled in tighter and tighter with a higher and higher electron, or a higher and higher oxidation state, a higher charge. When that happens, it results in a better overlap of the metal orbitals with the ligand orbitals, and that increases the energy separation between the d suborbitals, between the destabilized and the stabilized. So, a higher charge on the metal ion, given that you're comparing the same metal, results in a greater separation. Okay? And finally, the nature of the ligand. So the ligand molecules themselves have different charge densities. We talked about what that is. It's basically a ratio of the charge versus the size, the overall diameter or radius of the substance or the particle. The greater the charge density, the closer the ligand will be to the metal ion. It will have a more stronger attractive forces, and the better the orbital overlap will be. That results in a higher charge separation or crystal field separation energy. Okay. Now, would we expect you to know right off the top of your head the charge densities and all of this? No, we would not. Okay. A Japanese chemist by the name of Tsushita arranged the ligands based on experimental data, experimental evidence, into something called the spectrochemical series. And it's based on the order of increasing charge or separation energy. This is in the IB data book, the new one. Now, I just downloaded and I printed off a copy for myself. I will upload this, so it will be on Schoology for you. If you wish to download that, that's fine. Anything that we would do from a quizzing standpoint or a testing standpoint that relates to this, I would provide you with this. I just simply cut and pasted it from the digital version, and here it is right here. The way this is outlined, we have these are all a series of ligands. The strong field ligands, the strongest ligands, are at this far end here. The weakest ligands are at this end at the left. So that's outside here. The series is arranged from weak field ligands on the left, increasing to the strong field ligands on the right. The stronger the ligand, the greater the energy separation. So in other words, if given everything is equal, let's say I've got the Fe2 plus ion, and I am going to surround that with 6 chlorides. So I got a hexachloro iron 2 complex versus a hexaamine iron 2 complex, meaning I'm surrounding it with 6 ammonia. The ammonia complex will have a greater energy separation than the chloride, because it's a stronger ligand, and therefore will result in a better overlap of the orbitals and a greater separation. You see how that works? So we're not really memorizing specific examples. We're memorizing, if we want to think of it that way, the trends, so that we can figure out, comparisons based on those trends. Okay? So at this point, the question then comes up, so how does that all relate to color complexes? And I've kind of alluded to it already. So let's just kind of get into this. As long as the d-block metal has only partially filled d orbitals, there is a potential for a stabilized electron to become excited and absorb energy and jump to the higher energy destabilized orbitals. But you got to have it so that it's only partially filled. There's got to be room somewhere in there for those electron exchanges to happen. Okay? So therefore, something like the copper 2+ with the configuration, the argon core 3d9, although it's very close to being full, it still has one open spot that you can have an electron move up into. So it has an incomplete d sublevel, and so when an electron jumps to the higher destabilized orbitals, it absorbs energy in the visible spectrum and has a blue crystal color and a blue solution color. We contrast that with something like zinc 2+, which has the configuration argon 3d10. Now, there is no room. The d orbitals are completely full. There is no room for a stabilized electron to move to the destabilized orbitals because they're already all full. So, as I've said here, there are no open orbitals for the d orbital to d orbital electron jumping, and therefore there is no opportunity for the energy to be absorbed. Therefore, the zinc 2+ is not colored, appears white as a crystal, forms colorless solutions. We okay with that? It's why we don't consider zinc to be a transition metal. For the same reason we don't consider scandium. If we were to do the exact same comparison with scandium, scandium only forms a 3+ ion. There are no electrons in the d sublevel to be able to make those transitions, those jumps. So although the d sublevel might split, we don't even consider it because there are no electrons to be able to make those transitions anyway. So scandium is not a transition metal either. Okay? So as I said here, white light consists of all the colors in the visible spectrum. If we take them, mix them all together, we get white. As stated above, transition metals have the ability to absorb some of the wavelengths that correspond to these colors when the electrons jump between the stabilized and the destabilized sublevels within that d orbital. And what we see, and here's the key, what we see are the wavelengths that are not absorbed. What we see are the ones that get through. Okay? So the complementary colors is what they're called. We can use the color wheel to determine the complementary color of any absorbed wavelength. Color wheel is on page 15 in your data book as well. Now I've had to kind of shrink it down a little bit to fit it on the screen, but you get this color wheel on the left in the data book. Get this color wheel on the left in the data book. You can certainly see how you have upper and lower limits in terms of wavelengths for the different colors. So 400 to 424 nanometers is violet, 424 to 491 is blue, 491 to 575 is green, 575 to 585 is considered yellow, 585 to 647 is orange, and 647 up to 700 is your reds. And so the neat thing, and then this color wheel here was taken from the companion guide. It's got a little more colors. It doesn't have the wavelengths here, but it is giving you a little more colors. So you've got green, you've got yellow, a mixing of green and yellow. So yellow-green, you've got blue-green, you've got blue-violet, you've got red-violet. So you've got some mixing where there's a bit of crossover, blending one into the next. You would get this color wheel on anything for testing and those types of things. The complementary color on the color wheel is the color opposite to the color absorbed. So if a D block metal complex absorbs yellow light, which is here, the complementary color would be violet. And so that substance would appear as a violet color, purplish, right? And we can see from this, and from what we already know about atomic spectra, that the color of transition metal complexes is a measure of the energy of a photon that is absorbed, and that this relates directly to the crystal field splitting energy. So we can kind of work backwards. We go, oh, well, this is blue. Complementary color to blue would be orange, which means that's the color that was absorbed. So we can then say, okay, well, if we were to take the average, or we were to take the middle, the mean wavelength here, and say that's the wavelength that was absorbed, we could then calculate the energy, or we could calculate the upper and lower limits of the energy that's being absorbed from the color that we're seeing. The upper and lower limits of that energy represent the upper and lower limits of the separation, because what we're seeing, we're relating directly the energy absorbed to the crystal splitting energy. And we can calculate that energy using Planck's equation. So that's all I've said here. Since the color of any complex is dependent on the splitting energy, the color of any complex is dependent on all three factors that affect the size of that energy. We can also use the color of a complex to determine the wavelength of light absorbed, and thus the energy of that photon using Planck's equation. E equals hf, right? And h is Planck's constant, f is your frequency. You can figure out frequency from wavelength. So you use the universal wave equation, C equals lambda f. Calculate f based on lambda, the color of wavelength that was absorbed. You can figure that out from the color that's being emitted, that you see. And from that, we can calculate the energy of the photon. And as I've said earlier, this can be inferred by the crystal field splitting energy for that transition metal. Any questions with any of that? That's how we get these, first of all, these colors, and second of all, how we can use these colors in that analysis along with the color wheel and Planck's equation and the universal wave equation to calculate the energy that is being absorbed and therefore the splitting energy. So this is, we know that, if we go back here and we say, well, it absorbed orange, then we know the splitting energy is a minimum of whatever this wavelength works out to, and a maximum of whatever this wavelength works out to. It's going to be somewhere between this much energy and that much energy, because that's the entire spectrum that's orange. You see what I'm saying? It's kind of neat. All right. Any questions?